by answering the research question. What is the effect of square feet on list price after taking into account all other what predictors? Well, to answer that question, we can go to StatCrunch. So I'm going to head over to StatCrunch and I'm going to go to statistics, go to regression, go to multiple linear regression. My interest is to predict list price based on square footage, age, bedrooms, bathrooms, and number of garages. So I am looking at this first data set. And in particular, if I want to calculate the effect, taking into consideration what we call sampling variability, and I do not just want the hypothesis test, I would like the confidence interval for the estimates. I can set the confidence level. If I want 99% confidence level, I only need to change this to 0.99. But for now, I'm going to go with the default value, which is 0.95, and compute. What you notice is that you don't only get the estimates of the effect, you also get the 95% confidence interval for the regression slope corresponding to the square feet. And let us see what this number means in the context of the research question that we seek to answer. First of all, we notice that that interval does not contain zero. What does that mean? The fact that it does not contain zero means that the effect of square feet on list price, even after accounting for sampling what variations, does not include zero, which means that square feet does not have zero effect on list price. It has a tangible amount of effect on the list price. And to estimate that, um, we want to estimate the size of that effect. And the size of that effect on average is 63.06. Take note that this number lies in this interval. So in the output above, we have that interval, which I've written here, which is a 95% confidence interval for the effect of square feet on what? The list price. And since that interval does not contain zero, we conclude that square feet has what? A statistically significant effect on list price. But that still leaves a question. How big is the effect? To answer that question, we say that for every 1 unit increase or 1 square footage increase in home size, we can be 95% what confident that I meant to write confident here. Confident that the list price would increase. How do I know it's going to be an increase? That is because the interval only contains positive values. There are no negative values. So I expect the list price to increase by as much as about $55.16 to about $70.97. In that way, we have answered what? This research question. Let's proceed to yet another concept, namely collinearity. You might notice that in this regression, in this multiple regression model that we're fitted, we have quite a number of independent variables, which of course is what makes it what a multiple regression what model. And the point to note here is there might be the possibility that square feet is having an interaction with what age, or age is having an interaction with bedrooms. And if the information provided by square feet in predicting the list price is about the same information that age is providing in also what predicting the list price, then we have redundant information included in this model. When that happens, it can bring a lot of what negative effect on the validity of our model. So collinearity refers to a situation in which two or more predictor variables, take note, not the y variable, not the response variable, but strictly speaking, two or more predictor variables are closely related to one another. In particular, collinearity is the simple case where two predictors in our model are highly linearly related. In other words, in everyday parlance, that is saying that those predictors offer about the same information in explaining variations in your response variable. Multicollinearity is a more expanded, messier version of collinearity where three or more predictors are linearly related in some combination, which might not necessarily be pairwise. Now, why are we concerned about collinearity? It is because they can pose problems to the quality of our model. For instance, it might make it difficult to separate the effect of square feet from age on the list price. And our whole goal is to actually what? Separate those effects. That is our most desirable goal. We want to see what the individual effects of the explanatory variables are on the response variable, namely the list price. And another issue is that when we have issues with collinearity, the coefficient estimates, like the value we got here, may not be stable, and the standard error may also become what? Really big. And when the standard error gets big, that's a signal that the error is not as accurate as we want. Increasing error means what? Decreasing accuracy in predictions, and also in making an informed explanation of the variations in the response variable. So, how do we detect when we have what? Collinearity or multicollinearity? A basic tool that we use in statistics is to use your correlation matrix. I can see that in the case of age versus what? Square feet, this is a relatively weak what? Correlation, which is good because it means that age is not offering about the same information as the square footage of the house in predicting the list price. But if you look at bedrooms and square footage, this makes sense because, of course, the more the bedrooms, the more the what? The more the square footage of the home. And this is relatively large. We ideally do not like this because this would be telling us that, well, if square footage is already telling you whatever information that square footage is already providing in predicting the list price, bedrooms is offering just about the same information. That leads to what? Inclusion of redundant information. So we suspect in this case that there is collinearity between square footage and what? Bedrooms. I am not surprised that with bathrooms and what? And square footage too, this is relatively sizable. So we might have an instance of multicollinearity here. Now, sometimes it might be difficult to assess what threshold that we should establish in order to say, oh, there's multicollinearity. Is it when it's past what? 0.71? Is it when it's past 0.72? That can be what? A little bit of a challenge. When that happens, in practice, we can compute what we call the variance inflation factor. The variance inflation factor has this formula. And you see, as a rule of thumb, if the variance inflation factor for a particular independent variable exceeds 5, then it might indicate that we have a problematic amount of collinearity. And one redress in that case might be to drop one of the variables. For me, in this case, for instance, bedrooms and square footage, I might drop what? Bedrooms. And one of the reasons why I might drop that is, let's look back at the model. Did you notice that for list price, if we're going to predict list price based on the number of bedrooms, I would expect that as the number of bedrooms increases, the list price should also increase. Did you notice that the effect here is negative? This is a very good signal that there are multicollinearity issues because as the number of bedrooms increases, intuitively, we expect the list price to also increase. So this negative is a red flag. So it might be an indicator that I should remove bedrooms from the models because square footage already provides what? The same information that I need. And let's go on to the last research question for this video. In this case, I would like to quantify the amount of variation in the list price that can be explained by the model after taking into account all the independent variables included in the model. To answer this, we need the coefficient of multiple determination. That is R squared here. R squared is the sum of squares regression, which is highlighted in red and provided in your analysis of variance table. And that is 1.03889 times 10 raised to the power 12. So this E12 means times 10 raised to the power 12 divided by the total sum of squares, which is in green here. That is 1.2730326 times 10 raised to the power 12. And that will give about what? That will give 0.8161. What does this mean? 81.61% of the information, of the total information that we need to predict the list price accurately was provided by a combination of what? Square feet, age, bedrooms, bathrooms, and number of garages. Okay? With that said, we also want to take note that we have the R squared adjusted. Why do we need the R squared adjusted? It is because, you see, as you include more independent variables or explanatory variables in your model, the R squared will keep increasing, even if the independent variable you have included offers no real value in predicting or explaining the response variable. So the R squared suffers from this limitation. To overcome that limitation, we devise the adjusted R squared, which penalizes for the inclusion of an irrelevant independent variable in your model. And so it does not just keep increasing without what? Limits, even when you include useless or intangible or not non-useful independent variable. So this is really, really critical. The R-square adjusted is also useful for comparing different models fitted to what? To the same data set for explaining the same response variable. Very, very important.